Okay, salam, salam guys. I hope you are doing well, and welcome to lecture 9. And in this lecture, we will study human body antennas. Okay, that is a very important and very interesting topic. Okay, to know. Okay, so today we will briefly discuss about human body antennas, and I hope you will really like this topic. And I want from you to work on these type of antennas, okay, human body antenna, because in these types of antennas it is easy to target IEEE journals, okay, because you are here you are implementing your antennas for human body applications, okay, for a real-time application. That's why if you simply design antennas, it is hard to publish in IEEE journal, but if you utilize your antenna for practical application, then it is easy to target IEEE journals, okay. Okay, so let's open any research paper and then we can follow, okay. Okay, so this is a paper on human body antennas, okay. Actually human body has of 3 types of applications, okay. Human body antennas have 3 type of application. The first one are called on body antennas, okay, on body antennas, okay, and the second one is off body antennas, of body antennas, okay, and the third one are in body antennas. Okay, combinedly if you study these 2 types, then it is called wearable antennas, okay. Wearable antennas, okay. And for the third type, it is also called implantable antennas, okay. Implantable. Okay, so you can see we have a now we are going to study human body antennas, okay, that has 3 types: on body antennas, off body antennas, and in body antennas, okay. And the first 2 types are called wearable antennas, utilized for wearable applications, and the third one in body antenna for implantable medical applications, okay. So today we will discuss these 2 types, and the third type we will discuss tomorrow, okay, in brief detail, okay. That is very important type, okay. So let's start with this one. In wearable antennas, okay, we have a on body and off body, okay. So if we study about the on body, we have on body and we have off body, okay. You can work on these type of antenna like on body antennas and off body antenna. If you want to work separately, you can also design antenna only for on body application, okay, or if you want, you can only design antenna for off body application, okay. So what is the difference between on body and off body antennas, okay? The main difference is that in on body applications, both antennas are utilized for human body application, but just the difference in the radiation pattern, okay. Like for on body antennas, the pattern of the antenna must be omnidirectional pattern, okay. And while in the case of the off body antennas, you should have wait a minute, this is okay, you have a omnidirectional pattern, and in the case of the off body antennas, your pattern must be directional pattern, okay, in the upper side, okay, with some there can be some lobes, okay, back lobe I mean. But in the case of the on body antennas, your pattern must be omnidirectional, okay. omnidirectional. Okay, and in the case of the off body, your pattern is directional pattern. Okay, it can be directional, okay, or it can be broadside. Okay, broadside. Okay, so for those who just joined now, I am describing that in this lecture we are going to study human body antennas. Okay, and human body antennas are of three types. The first one is for the on body antennas, the second one is off body antennas, and the third one is in body antennas. Okay, the first two types can also be called wearable antennas. Okay, while the third type is for utilized for the implantable medical applications. Okay, and it is also called implantable antennas. Okay, that can be inserted inside a human body. As you can see here, it is on body, means on body, like we have a chest. Okay, so it means on body case we utilize the antenna on chest. Okay, the part of the main body. Okay, while in the case of the off body antennas, actually in most of the papers you will see researchers are combinedly study these type of antennas. Okay, on and off. Okay, like it can be utilized in many ways. Okay, like you have a human body structure here, like this is, suppose this is your human body, and you have utilized the antenna or kept the antenna on human body. Okay, like this is on body antenna. Okay, this is your on body antenna. Okay, and what it will do, it must have omnidirectional pattern. Okay, it will give you omnidirectional pattern like this. Okay, okay, suppose it is giving radiation, and it is reflecting. Okay, suppose you have designed this antenna at 2.45 gigahertz, and why I am always say that you design the antenna at 2.45 gigahertz, because in human body antennas there are some specific frequency bands that are can be utilized for the human body applications. Okay, what are these frequencies? The first frequency is 0.402 megahertz. Okay, this is the first frequency that can be utilized for the human body application. The third one is the this is not 402 megahertz. Okay, the second one is the 915 megahertz. Okay, I mean the most commonly used frequency bands. Okay, the third one is 2.45 gigahertz. Okay, and the fifth one is 5.8 gigahertz. Okay, and the fifth one is the 24.125 gigahertz. Okay, and the other one is 64.25 gigahertz. Okay, these are the most commonly used frequency bands. Okay, but the most widely used bands are these one. Okay, this is called ISM band. Okay, ISM band, it is called mixed band. Okay, MICS. Okay, the ISM bands are these one. Okay, below or above. Okay, ISM, industrial, scientific, and medical band. Okay, in this way, let me find a data sheet here. You will see the applications. ISM band, there are so many other frequency bands. Okay, you can see here and check their frequency range. Okay,
Mr. Ahmed.
yes,
I want to ask you about why they choose on-body omnidirectional and off-body directional.
okay, I will explain. Okay, first I am describing the frequency bands. Okay, at which frequency I tell you to work on it. Okay, you can see there are so many. This is ISM bands. Okay, many ISM bands. but the most widely used bands are these one, okay, these one, okay. But I suggest you to work on this band, okay, or this band, okay. You can choose these, only I suggest you only two, okay, these two bands, okay. The operating band is frequency is 915 megahertz, okay, and 2.45 gigahertz, and it should have or must have the bandwidth more than, if you are designing on 915 megahertz, then I suggest you to keep your bandwidth more than 26 megahertz, okay. And in the case of this band, you must have bandwidth more than 100 megahertz, okay. So this is most commonly used, and I suggest you to work on these band, even for all these type of on body, off body, and in body, okay. I suggest you to work on these two frequency bands, okay, because in this frequency band you will find many papers in which you can compare your results with the previous research, okay. Also there are a lot of paper available because a lot of research has been done on these, on this frequency band, okay. And why people are prefer to use lower frequency band, because in the lower frequency band the size of the antenna will be very large, okay, but the people are working to reducing the size even at the lower frequency band. That's why they prefer to use lower frequency band, okay, like 915 megahertz. Okay, so in on body case and off body case, in on body case we have omnidirectional radiation pattern. If your antenna gets omnidirectional radiation pattern in E plane, okay, not in H plane, E plane, okay, because in H plane most of the antennas have omnidirectional radiation pattern, but I am here talking about E plane, okay. In E plane the pattern of the antenna must be omnidirectional for the case of the on body, okay, and in the case of the off body the pattern must be directional or broadside, okay, broadside and along E plane, okay. And you cannot say that in E plane your antenna has directional radiation pattern, so it is called off body, but in the case of H plane your antenna has omnidirectional radiation pattern and you can say it is on body. This is not I am telling you, okay. I am talking about here E plane, okay, in both of the cases, omnidirection in E plane and direction in E plane in off body case, okay. So just keep in mind, okay. Okay, in the case of the on body, you mostly in most of the research you have you can implement the or place the antenna on the human body, okay, or like on chest, okay. And also in some of the cases people like to place the antenna on human hand or human arm or human leg, okay, like this. But in some of the papers I saw that, realized that some people say off body antenna sometimes they do not place the off body antenna on the chest, okay. They mostly place this antenna off body antenna on the leg, on the arm, okay, like this, and it has a directional radiation pattern, okay. So in most of the cases people like to work combinedly on body and off body, like if you have a dual frequency band antenna like this one, okay, you have suppose operated this antenna at 2.45 and 5.8 gigahertz, okay, 5.8 gigahertz. If suppose at one frequency band if your antenna shows omnidirectional radiation pattern, then you can say at lower frequency band your antenna is on body, behaves like an on body antenna, okay. While at the high frequency band if you notice the directional radiation pattern, okay, then you can say your antenna behaves off body antenna in at high frequency band, okay. I will show you my paper in which I will show you two papers. In the first paper, if you complete notice the you can see here I am just talking about here off body antenna, not on body antenna, okay. Because here I am using meta surface, and meta surface helps to make the pattern directional radiation pattern, okay. That's why in off body antenna I mean in with the meta surface it is easy to achieve off body antennas, okay. like at first the pattern of my antenna is like this. Okay, you can see here in the E plane it behaves like this. Okay, yes, at at 2.45 gigahertz, I mean. Okay, this is uh, this is at 2.545 gigahertz. Okay, and this is at 5.8 gigahertz. Okay, and you can see here at 2.45 gigahertz it is just like a bidirectional or dipole. Okay, uh, blue one is the E plane. Okay, the red one is the H plane. Okay, and when I use the meta surface, then you can see the pattern became the direction radiation pattern. Okay, this one. Okay, so you can see here it is direction radiation pattern or broadside. Okay, so in all of the cases it is a directional pattern. That's why I said that my antenna behaves like off-body antenna. Okay, or can be used for the off-body application. And in this paper I test the antenna on a human hand. Okay, like this one. This is my hand. Okay, and I test the antenna on a human hand. Okay, so did you understand the concept of this on body and off body?
Mr. Ahmed, in case of on body,
Yes.
Isn't harm for human body?
Yes, this is a question. Okay, yes, actually, first you need to design the I mean operating frequency, the operating band that is utilized for the utilized for the ISM bands. Okay, industrial, scientific, and medical band. They have said that at these frequency the antennas are less harmful to the human body. Okay, but keep in mind whenever you design the antenna, you need to calculate the SAR values. Okay, you can see in my paper I have calculated the SAR values. SAR values tell you about the how much antenna effective to the human body. Okay, what is the concept of the SAR? Actually, SAR value, let me write here. SAR stands for the scientific absorption rate. Okay, okay, and you know, it is the absorption rate value, how much radiations are absorbed by the human body. Okay, so it will tell you about this one. Okay, and if you are testing the antenna at 10 gram, okay, of mass of mass, then its value should be less than I think 2 watt per kg. Okay, but in if you yes.
Excuse me. If you show us a table for the limitation for the SAR, it will become good. Or you can send us if you have a PDF file for the limitation for the SAR for the safety.
There are two rules only of this. I am writing here. Okay, just keep in mind these two things. Okay, if you are testing the antenna at 10 gram of mass tissue, then your value must be less than 2 watt per kg. Okay, and if you are testing the antenna at 1 gram of mass tissue, then your value must be less than 1.6 watt per kg. Okay,
so is it in any place in a human body?
yes, on human body.
Because I guess maybe the head has some maybe some requirement, hand is different requirement, chest have a requirement also. I guess that.
Yes, in some of the I mean this is on body cases. Okay, like if you are testing on chest or but in the case of ear application it is the same. Okay, but in the case of the implantable antenna it is different. Okay, because the antenna is working inside the human body.
Okay, so.
Okay, just keep it.
Sorry, Mr. Ahmed, but I think in every country it has different value of SAR.
SAR. Yes, but this is according to the IEEE standard. Okay. IEEE standard. I will download a table and will send you. Okay, what are the requirements? I mean, according to the country, it may varies. Okay. I think this is I think in USA. Okay, United States, and this one I think in Europe. Okay, this in European countries.
So in this case, I think off body is better than on body.
Wait a minute, this, sorry, this for 10 gram it is for Europe, okay, as it is written here, you can see here, for Europe it is 2 watt per kg, okay, and it is 1.6 watt per kg in which country they did not mention.
FCC, I think it's the standard of FCC.
Yes, Federal Communication.
Federal Communication, I think communication community, something like this.
Yes, same.
I think it's American standard.
Yes, this is according to FCC, okay, and this is according to the IEEE, okay, the above one. Okay, there was a question before, I forgot what was the question.
I mean, in this case, off body is better than on body because it don't harm the body, human body.
Actually this is both of the cases, okay, like in both of the cases you should have values, you should have less than these values, okay, so both are acceptable, both are good, both have a same, but in research people like to focus on the on body antenna, okay, it is very important than off body antenna because it is not easy to achieve the omnidirectional radiation pattern on E plane, okay, so it is you need to modify the structure and do so many things to make your pattern omnidirectional, okay, that's why it is very important.
Do you have a diagram or graph for broadside in the radiating E plane?
Yes, this one you can see, this is my paper, I will send you on WhatsApp, okay, you can see here, this is showing direction radiation pattern, okay, broadside, directional, broadside, okay, broadside and directional in the upward direction, okay.
And in CST, how I got it?
In CST, in most of the cases, okay, I will today I will also give you some tips to make your antenna omnidirectional or directional radiation pattern, okay.
Okay. Mr. Sarosh.
Yes.
Please, for the, if you are measuring it practically on a human hand, how are you able to know that you are measuring for 10 grams and 1 gram?
Actually, this is only possible in simulations, okay, you only check the SAR values in simulation, also you can calculate the values by formulas, okay, like in suppose if you are first if you are simulating this antenna in CST, then there are some equations, let me show here. Yes, these are the specific absorption rate values, okay, and you can calculate these values, okay, by these values, okay, you should know the thermal conductivity and the mass density, okay, how much mass you are using, okay, and the electric field intensity, okay. So if in practical case you should test the thermal conductivity and the mass density of the human body, and you can just write the values inside this formula and you can easily calculate the SAR values, and then you can compare with the simulated ones, okay.
Okay. Maybe show us in CST how we can manage this equation, please.
In CST we cannot use these equation, but in CST there is a option where you can calculate the SAR values.
So you use the SAR template, yes?
What?
The built-in equation in the SAR, yeah? In CST.
Yes, there is option in CST that you can find the SAR values, okay. I will show you everything you need, okay.
Because I think the people they put the equation also in the paper but didn't use as usual.
No, yes, actually there are many ways, like if you don't want if your system, because in most of the system they are not compatible to calculate the SAR value, so some people like to calculate through mathematical equations, okay, both are good, okay. so you can use any if you want. In yes in it is better to add the equations, because you know the specific absorption rate values are mathematically approved. Okay, that's why.
You can show to us also how to can manage this equation in CST, please.
As I told you, there are no equations in CST, but there is an option to calculate the SAR values. Okay, so let me open my CST.
Okay, thank you.
So today we will yes.
Good afternoon, Mr. Sarush.
Yes, good afternoon.
I want to ask about, do you know the human body is consistent of the multi-layer, like skin, muscles, fat, and everything. Do you have any information about which each layer that affected the frequency?
Okay, so first let me answer of this question. There is a website. This website, I will send you the link. Okay, let me send here now. I send on the WhatsApp. Okay, and you can open this website. Okay, and you can calculate the many things. Okay, like relative permittivity and electrical conductivity. Okay, and how you can calculate, you can see there are lot of human tissues that you want to calculate. Okay, like if I want to calculate the skin, let me write here skin. Okay, this is skin. Okay, and now what is the starting and ending frequency I want? Like I want from I want to calculate at 915 megahertz, then I need to set the range. Okay, you can also set this range. Okay, that you are using here, 902 to 928. Okay, 902 megahertz to 928 megahertz. Okay, so click on the go, and you will find options here. Okay, and you can see you will find at each frequency. Okay, like if you want 915 megahertz, then you will find here. Okay, this is okay, so this is for skin. Okay, this is 41.3 the relative permittivity, and the 0.872 of electrical conductivity. You just take these values and insert in the CST. Okay,
Can we find the penetration, the distance penetration? Maybe do you know this is this values that or this microwave that affected mostly effective in the skin, but maybe ineffective in other layers. Could you find the penetration distance for the electromagnetic field?
you mean how to calculate the distance? You mean what distance should we take from the human tissues, the antennas, and the distance between the antennas and the human body?
Yes, maybe I want to affect it, only the muscles, don't affect it, the blood, because maybe some maybe affected in the molecules of the blood. So I want to just the muscles, or I want to just affect it to the fat to burn it without affected to the like this. So I want to need to calculate the skin depth and the penetration distance.
Also there are some websites to calculate the skin depth. Okay, skin depth calculator, or you can also calculate through mathematical equations. Okay,
Mr. Saraj, can you send us the link of this that you use it?
what?
Can you send us the link?
Yes, I for this one I send the link on the WhatsApp. Also I will send by email. Okay, and for this one too. Okay, you can calculate the skin depth from this website. Okay, let me copy this and you can send you on WhatsApp. Okay, the upper link is for the calculate the relative permittivity and the electrical conductivity of the human tissues, and the other one for the skin depth. Okay, okay, so let's open CST, and let me tell you how to implement this antenna. I mostly like to work at 2.45 gigahertz, okay, that is ISM band. But in implantable antenna I like to work at 900 megahertz. I had some CST file, let me open so that time will not be wasted more. Yes, this one. This is the same design that is published in this paper, okay, the same design. Okay, here I have used multi layers, okay. This is a metamaterial, okay. Let me delete metamaterial so that you will not confuse now, because you don't have knowledge for the metamaterial now. Okay, so suppose we have a dual band antenna, okay, and we have a skin tissues inside the, human tissue behind the antenna, okay. What we have a jeans material, okay, of thickness 0.6 millimeter, and that has a relative permittivity of 1.85 and electrical conductivity of 0.085, okay. The first one is the genes, because this is like a wearable or a human body antenna, and when you implement the antenna on the human body, and you will surely wear your clothes, okay, and you will place your antenna, and there will be a cloth between your antenna and the skin, okay. Like in this paper, let me, like this one, okay. You can see if you implement your antenna on a human hand, then there is a cloth between your human tissues, human body and the antenna, okay. That's why I use sometimes jeans material, or you can use other cotton or other material of the cloth, okay. So that's why I use here jeans material, okay, of thickness 0.6 millimeter, okay. And then I use the skin tissue. You can see this is a layer of the skin, okay, that has the relative permittivity of 41.4 and many other, okay. And then I use the fat, okay.
There is no also website for I think the properties of the textile material.
For the textile, actually there is I think no website, but because the properties of the textile material will be the same even if you are designing antenna at different frequencies, okay. So it is the same, and I just take these values of the genes, from research paper, okay, from a published research paper. You can read the some research paper, and you can see how and what are the values they are using, okay. Okay, then we have a first we have a skin, and then we have a fat muscle, okay. You can see here, and I also want to tell you what should be the thickness of these values, okay. Like for the jeans, its values mostly in case is 0.6 mm, okay. Okay, and you can if it depends on your antenna size, that how much should be the size, okay. You can take its area 100 cross 100 millimeter square, okay. This is for the jeans, okay. And for the skin, the thickness you can take between 1 to 2 millimeter, okay. And for the fat, you can take its thickness between 2 to 5 millimeter, okay. For the muscle, you can take thickness between 5 to 10 mm, okay. Here I prefer 1.6 mm, okay. And here I prefer 3 mm, and here I prefer 8 mm, okay. Okay, so you can take these values, and I also prefer you, if you are working on human body antenna, then you need to simulate only these tissues, okay, skin, fat and muscle, okay. Do not include other materials of human body or other tissues, okay. So it will not have much effect, okay. Okay, so and then we have a muscle tissue, okay, at the end. And also, you know, this is your front view of the antenna, and in the back view of the antenna, you should need to keep human tissues on the other side or on the back side of the antenna, okay. Okay, and for the SAR values, I did not simulate these SAR values in my laptop. I just or in on these human tissues. Sometimes CST simulate on these human tissues, and sometimes does not simulate on these human body layers, okay. So for that you need to import the other data, like a complete human body model, and then you can calculate inside CST, okay. I For the S11 and the radiation pattern you can calculate, but I am talking about the SAR values, okay. So in this SAR values you cannot calculate, okay. Like I am going to simulate this one, and we'll check its results, okay. And then we will because in order to calculate the SAR you need to simulate this file first, okay. And then this option will become enabled for you, okay. In the post processing you will find option SAR, okay. Sorry, let me stop this one. Before going to simulate this one, you need to go to the simulation and then go to the field monitor, okay. And then you need to go to the power loss density and SAR. In this option you will find SAR values, okay. At which frequency, 2.45 gigahertz, okay. Click apply, and then 5.8 gigahertz, okay. Click apply, and then simulate it. So today I will show you how to calculate the SAR values, okay. In my laptop it will not simulate, but I will tell you the complete procedure, and I will tell you how to run simulation for the SAR, okay. It will give you some errors, but I will tell you how to solve that errors, okay.
Professor Sarosh,
Yes.
please, the values for the skin
I think the fact that you listed, does it actually reflect the sizes of the actual human body, like real human body? Does those sizes reflect actual human body?
The size of the human body, I prefer you to use the 100 cross 100 millimeter square area and the thickness that I described here. Okay, you can use this thickness. Okay, and if you can increase or decrease the size of the human body, it will not affect much. Okay, but you should use 100 cross 100. Okay, if you keep it less than 100 cross 100, then it may vary your frequency. Okay, a little bit but not more. Okay, because the properties are remain the same, just the difference in the size. Okay.
Okay, but I'm talking about the thickness. The thickness, is it the
Uh,
the value that you gave?
uh,
Does
you mean
it reflect
if you
actual?
keep other thickness like 1 millimeter or less?
Yes, yes.
Not I did simulation on it, but I did not saw any big difference in the results. Okay, but I mean in most of the cases, like if you want to implement antenna in practical way, then you need to keep these values. Okay, but there will be no any big difference in simulations.
Okay.
Is there any requirement to piece of PC to simulate human body model? Uh, for the you should have your hard disk more than 250 gigahertz. Okay, I prefer 500 gigahertz, and for the RAM must be higher than 8 GB. Okay, if it is less than 8 GB, if you have more RAM, then it will simulate very fast. Okay, if you have very less RAM, it will take more time. Okay, here you
Yes.
can
So
see it is taking much time.
so that's I think you mentioned that the size of the ma- the body does not actually affect the result that much, but when you increase it too much, it increases the simulation time, right?
Like if you want to implement the antenna, like if in practical way, like or if you keep the antenna on a human body, then it will you are not placing your antenna on the whole human body. You are just because in practical way, your size of the antenna will be very small. Okay, and then if you keep the antenna on a human hand, then you will see very small portion of the hand just covering by the antenna. Okay, that's why I told you to keep these values. Okay, so that it if you increase, how you can take more this is according to the size of the antenna. Okay, even you cannot place your antenna on your whole human body. You will know this portion of the human body will be covered according to the size of the antenna.
Okay.
Okay, I tell you how to show how design and how to place the one above the other layer for skin, fat and muscle multi-layer. Okay, here it is taking much time. So okay,
Ahmed,
yes,
if I have just 8 giga RAM, I can't simulate this.
you can simulate. I also have 8 GB RAM of this laptop.
Okay. Mr. Ahmed, can I reduce the mesh size? Maybe if it reduces the mesh size, we can use, we can gain more time, I think.
If you decrease the mesh size, then surely it will not take much time in simulation, but your results will not be much acceptable with the when you are going to fabricate your design and test in the measurements. Okay, you will
It's
see.
not accurate.
Yes, I do not prefer to keep less mesh size. Okay, I always suggest you to keep mesh size more. Okay, where your antenna, because if you have more number of mesh sizes, then your antenna will accurately give you results. Okay, because you see some people ask which software is more better for designing antenna, HFSS or CST. So HFSS is more accurate than CST because the mesh size, you can control the mesh size, and even you will have much number of mesh cells in HFSS, okay, and it give you more accurate results. But if you also increase the number of mesh sizes in the CST, then you will surely be able to get good results, okay, after measurements. Okay, so I am going to show you how to keep these layers one by one, okay, after the antenna. Like I am going to remove the human tissues, okay, like, okay, this.
And also Mr. Ahmed for E-plane and H-plane.
Okay. Okay, so this is my antenna. Okay, so in order to design the skin, fat and muscle tissues, you need to align your WCS according to the size mid of the substrate. Okay, as you see, I am going to the this is my substrate. Okay, if I click and double click, and you see now my WCS is in the mid of the substrate. Okay, now you need to go to the brick. Okay, click on the escape button. Okay, and you can write here gene. Okay, if you want to create a genes material, if you want to only skin, then you can write here skin. Okay, and you can write here 100 by 2. Okay, okay, and you can see here this is your skin tissue. Okay, and how much should be the value of the you can write here 1.6 millimeter of the skin. Okay, you can write here skin. Okay, in CST you will not find these options, okay, like genes, like skin, like muscle, like fat. Okay, so what you need to do, I created these materials myself. Okay, and then I wrote the name here. Okay, so how can we find the or create a new material? Okay, you need to go to the new material. Okay, and you will find here you can write here skin. Alright, I already have, so I write here skin underscore 1. Okay, okay, now I need to write the values it may varies, but at this frequency it is 41.1. Okay, and go to the conductivity. Okay, and you can take any value of this one. Okay, if you want, you can write the values for electrical conductivity, but if you want loss tangent, if you know the loss tangent, you can write here. Okay, but I prefer electrical conductivity. Okay, and it is 0.87. Okay, now I click OK, and you can see my new material has been created. I click OK.
If I write any value, is not affect on the result?
This is wait a minute, what you're saying?
I mean, if put any value
Uh,
on the material, is not affect on the result.
You cannot take any value. You need to first calculate, or you can you need to create a table. Okay, like in this way, in this design, you can see here not here, this one, there is a table, I think, for the human body. Yes, this one. Okay, you can see here in this table you know every values. Okay, like you know the value of the skin permittivity is 41.1. I calculated from the website. Okay, and for the electrical conductivity you have 0.89. For the fat you have this one. For the muscle you have this one. Okay, you know these values. Okay, okay, for the skin tissue, I forgot to tell you that you need to align your WCS on the other side of the substrate, not on the front side. Okay, but if you keep on the front side, then it will create a skin tissue on the front side. Okay, but we need on the other side of the antenna. Okay, that's why we are creating here. Okay, and just remove keep its direction like this, or if no worry. Okay, so you need to decide at which distance you want to create the skin. Okay, if your antenna is actually the size, the distance of the skin, fat and muscle tissues depends on the structure of the antenna. Okay, like suppose I have antenna. Okay, and I am using a full ground plane. Okay, I am using a full ground plane behind the antenna, behind the substrate. Then if you have a copper on the complete surface of the antenna, then it will not affect much on your human tissues, even if it is more and more closer. Okay, suppose in this paper, the other one, okay, this one, this is the antenna, dual band antenna used for the both application, okay, on and off body. This is my paper published in at MDPI sensors. Okay, so I show you, this is a very simple structure. Okay, you can see here there are just L-shaped slots inside to make two type of radiators. Okay, the first radiator is like a H-shaped radiator, and the other radiator is like a 8-shaped radiator. Okay, the H-shaped radiator works for the 2.45 gigahertz, and the 8-shaped radiator works for the 5.8 gigahertz band. Okay, so let's you can see here, this is a dual band antenna, and it is perfectly working at 2.45 gigahertz and 5.8 gigahertz. Okay, in each paper you saw I have added the design steps and the equations. Okay, and the parametric optimization you also need to do in this way. Okay, okay, you can see here in the E plane, your antenna is just very close to omnidirection pattern. Okay, just there is a little difference in this side. Okay, but it behaves like omnidirection. Okay, and this one is a broad-sided pattern. Okay, so that's why if it is more closer to the omnidirection or direction radiation pattern, then you can also claim that your antenna behaves like this. Okay, I am going to tell you that as you saw in this design, I have used the full ground plane. Okay, you can see here I have used the full ground plane behind the antenna, and in this way, if you have a full ground plane, then the human tissues will not affect much. Okay, even if it is very closer to the antenna. Okay, and you can see here I just directly place the antenna on the human tissue, and what is the difference in the results if I increase or decrease the I think I did not add here. I did not add in this paper, but in this paper, yes, I have added what is the difference if I increase the distance of the human tissue from the antenna. Okay, and you can see here this is the, yes, this is the graph. You can see if I place the antenna at 0 mm distance, then the antenna is still resonating at a proposed frequency bands. Okay, the frequency bands, I mean the antenna is not showing any big difference if even you increase or decrease the size of I mean distance of the antenna. Okay, if it is only in case if you have a full ground plane behind the antenna, but if you have a defective ground like this, then you need to increase the distance from the antenna. It can be of 5 millimeter, it can be of 10 millimeter, it can be of 15 millimeter. Okay, but it is more suggestible or more important to reduce the distance as much as possible. Okay, okay, I am telling you that if you using a defective ground, then you suppose you want to create the human tissues at the distance of 5 millimeter, then you need to shift your WCS first. Okay, at the distance of 5 millimeter, you can write here 5 millimeter and click OK. Now it is at a 5 millimeter distance. Okay, now you can create the skin tissue. Okay, so this is the skin. Okay, I created a new material. Okay, and assign the properties taken from the table in the research paper. Okay, this is the skin. Okay, now you can select the other side of the skin and create another material fat.
For creating the new properties for any material, I can select one of them, not both. The tan delta or conductivity.
Yes, you can select any one. You in the calculator you will also find electrical conductivity, not loss tangent. Okay, so you only need to calculate the electrical conductivity.
It can be applied for any kind, any material, yes?
Can you repeat question? I did not understand.
It can be done for any material. I don't mean the human body parts.
Yes, it can be done for any material. Okay.
Okay, thank you.
Yes, it is same for all materials.
Okay, thank you.
Okay, so you can see this is now I'm going to create a fat. Okay, this is the fat. Okay, and if I do not know the properties, then you go to the new material. Okay, go to the research paper and check what are the values they have used. Okay, okay, for the fat they have used 5.45 permittivity. Okay, so I write here 5.45 permittivity. Okay, and the conductivity is 0.049. Okay, 0.049. Okay, I write here. Okay, I also need to change the color because the color of the skin is this one. I need to change different color. Okay, so I can change different color here and click OK.
And for permeability, mu.
What?
And for permeability, I mean mu.
It is remain the same, one for all materials. Okay.
One for all materials.
Yes, you no need to change this one. Okay, because it is one, I think, for every material. Okay, let me check here.
Yes, it is one for any material.
Yes, you can see here. It is one. Okay.
Okay.
Okay, now we are going to create a muscle tissue. Okay, the third layer. Okay, muscle.
Excuse me, Professor, in your paper, I think you have maybe could you show me the table? I think you written about the density. From where you bring it?
Yes, for the density, I just read some research paper and got the density. Okay, if you want to write the density here. Okay, let me write here density. Okay, here I'm going to insert the properties of the muscle, and permittivity is 54.88. Okay, 54.88. Okay, and for the electrical conductivity it is 0.959. 0.959. Okay, and for the density it is 11 to 1. Okay, for the density you need to go to the density and write here 11 to 1. Okay, 11 to 1. Okay,
We must do it, or we can leave it.
What?
This is density. We must specify it or not.
Yes, you need to go to the density and write here the values.
No, I mean if we don't write anything.
That I prefer you to insert these values. Okay, then it will accurately calculate the SAR values.
But this part we can come we don't have our. We need only from the paper, yeah.
I think there is a. I will search for it. Okay, I send you. Okay.
The human body is different from
Yes. Here my laptop hang now.
No problem. Our simulation browser just show to us the SAR how we can dealing with it. Even
I will show you. Actually, the simulation is running. That's why it is taking much time. Okay, but
still running.
Mr. Sarosh, I want to know if any new research about the proprietary of the body.
what do you mean? New research topic on human body?
Yes, yes, I mean the body.
Okay.
Any new research about the proprietary of the body.
Yes, I can give you very important steps and very important ideas. Okay, because I like to you to work on, because this is an interesting topic. Did you like this topic or not? Because here you are using your antenna on some application for human body application. Okay, so that's why it is important to know, and also it is important to work on it. And as I told you before, IEEE journals accept these type of journals that is implemented for human body application. Can you send me the thickness of human layers? Okay, also you can take picture of this one if you want. Okay, you can take picture of this one. Okay,
I mean the other layers, Mr. Sarosh. Maybe needed the bone, or maybe they needed the
okay,
blood.
yes.
Some.
Yes, okay, I solved this problem for you. Okay, here I am using this tissues. Okay, and here the question rises, why I am using these layers, why I am not using human body model. Okay, it depends on as I told you, it depends on the compatibility of your computer. Okay, suppose my system can simulate only layers. Okay, so that's why I am using here these types of layers. But if your system wait a minute, my screen is not sharing you.
Yes.
It
Yes,
is,
it's severe.
okay, wait a minute, let me connect again from the computer.
I think also the Voxel model and the CST is just have two frequencies. One megahertz, and the second frequency is 900
Yes,
megahertz. Around
yes, you are right.
So there is the Voxel model. There is no have other frequency 2.45 gigahertz.
Yes,
Important.
yes. Okay, now
Any method to change this frequency for the Voxel model, or just maybe manipulated another one, or publication another one?
okay, yes, I understand you. Okay, let me find any CST file that is already simulated. Okay, so that we can simulate. Okay, yesterday I was doing for the I was calculating the CR values. Which one? Let me find a CST file that is already simulated, so that we can directly calculate the SCR values. Okay, and okay, okay, so here first we need to remove these human tissues. Okay, you understood the way of creating layers for the human tissues? Did you understand, all of you?
Yes, thank you.
Okay, for the human body model, now we are going to import the human body model where you can and one more thing, on the human tissues, on human layers, sometimes CST cannot calculate the SAR values, okay. Even if you want to, it will simulate your, it will calculate your S11 and other radiation pattern, but it will not calculate the SAR values because of these layers, okay. Because these layers are user defined, okay. I mean these layers are defined by you, not by the system, okay. So CST only simulate calculate the SAR values for that is defined by the CST, okay. That's why what we will do, we need to remove this one, okay, these layers, and we need to import the human body model. And then because that human body model is a part of this CST, okay, is defined by this CST, okay. So in some CST versions, like in cracked versions, you will find some errors, okay. I mean cracked version you will find errors, okay. So how to import the human body model? Here we are going to import the human body model, like you can go to the modeling and go to the import and export, go to the 3D files, and then go to the voxel data, okay. Click on the voxel data and you will find options here, okay. And go to the CST voxel family, click on it, okay. And you will find human body models for these type of, like for baby, for child, for dona, for ema, for gas stove, for this one, okay. In most of the cases we are going to implement at gas stove, it is the name of the person, okay, of a man, okay. So you can calculate, okay. Now you can see here, this is a complete human body model, okay. This is the front view and this is the side view, okay. There is a question in the chat box. Without simulating, can you show how to insert human body model? Yes, this is I am showing here, okay. Also show you how to place an antenna on a
Mr. Sarosh.
Yes, I will show you. Yes.
Sorry, just I want to. So there is no way to calculate SAR.
There is a way. There is a way.
With the material that I created.
Actually, for the layers, some laptops super laptops are required to calculate, like sometimes I send my design to Mr. Ihab. Do you know Mr. Ihab? He has a super laptop, and I sent him my files to calculate the SAR values, okay. But if you want to calculate SAR value by yourself in your PC, then I am showing these ways, okay, to how you can calculate the SAR values. So you need to import the voxel data that has the same properties or very close properties to the human tissue, okay. But it has all type of materials. You can see here there are a lot of materials here, okay, like brain tissue and many things, okay, here, okay. And also you can see here it is only calculate the 900 or 100 megahertz. I think we cannot change it.
Excuse me, Mr. Saroj, excuse me, could you start from the beginning? Excuse me, I'm sorry.
Yes, okay. This is your antenna, okay. And you need to go to the modeling option, okay. And then you need to go to the 3D files. You are importing the file, okay. That's why you need to go to the 3D files and go to the last option, okay, voxel data, okay. Click on it, and then you will find a CST voxel family, okay. So you need to click on it and you will find a family here: baby, child, dona, ema, gas stove, okay. This is a family, okay. Like in family we have a baby, we have a old man, we have a old mother, okay, and grandma, I mean, and we have a man and woman, okay. So gas stove is a man, okay. Baby, we have a baby, we have a child, okay, we have a donor and many other, okay. So we are here, we are going to select the gas stove, a man, the name of the man, okay. So click on it, click OK. You will find this one, okay. You can see here this is a complete human body model, okay. If you want to select, then you need to you can take this value, okay. If you crop this one, then it will only take this portion, okay. If you select all, then it will take the complete human body model, okay. And this is the front view and this is the side view, okay.
And for the frequency,
for the frequency, it is only for one, okay, 100 megahertz and 900 megahertz, okay. I think we did not change the frequency here.
I think you must import human body for that work in the frequency that you want.
Yes, okay, I will show you here. Okay, don't worry. Okay, I am showing here that if you want to you see there are a lot of materials here. If you want only selected materials, like you click on the all material and you can select only that you need. Okay, like if you need a blood, if you need click on it. If you need a fat, click on it. If you need skin, here I think, yes, you click on it. If you need a muscle, then click on it. Okay, so if you only need this one. Okay, and if you after this you need to click OK, and it will give you error like this. Okay, biomodel key problem. Okay, so how to solve this problem? Okay, in CST cracked version you will find issue like this. Okay, for that you need to download one more file. I will send you by email and by WhatsApp. Okay, like this one. Okay, let me show you here. This is another file. Where is this? Sometimes I forgot where I place this file. Okay, this one. Okay, I will send you this zip file. Okay, and you need to unzip this file. You will find like this. Okay, and you will have many options. Okay, but you are only able to import the voxel data. Okay, so this is only voxel file, while the other ones are text files, so you cannot import other files. Okay, so now go to the CST and go to the again modeling, go to the import, go to the 3D files, then go to the voxel data. Okay, and then click on the current directory, double click on it. Okay, and now you need to find the file where you have placed. Okay, so I have placed in my folder. Okay, now go to the CST human body. Okay, click on it and click on the human model. Okay, and you see there is a difference in this structure, but this is a human body model of a man. Okay, so this is a front view and this is a back view. Okay, sorry, side view. Okay, now you can see here we have many options. Also we have a 2.45 gigahertz. Okay, so you can take what you want. Okay, and for one more thing, you cannot simulate the whole human body model, so you need a very small patch, according to sorry, a very small portion of the human body where you want to calculate. Okay, because if you want to want to simulate a complete human body model, then you need a very supercomputer, more than 64 GB RAM. Okay, and 1 terahertz space and many others. Okay, okay, but here in most of the laptops, in most of the super computers, you are not able to simulate this complete human body model, so you need a very small portion. Like I'm going to here, like I want to simulate the antenna on the human arm. Okay, so I crop this human body model like this one. I am selecting only the hand. Okay, you can see here. Also click on the side view, and if you see there is it is selecting a hole, so we need to crop it like this. Okay, okay, I am clicking OK, and you can see this is your small portion. Okay, of your hand, human arm. Okay, human arm. So now you need to place the antenna on the front side of this one. Okay, so I do not suggest you to to shift your antenna towards the human body. I suggest you to move your human body towards the antenna. Okay, so in this option, in the voxel data, you will find option human model. Okay, and you can use the transform. Okay, and you need to you can transform it. Okay, and you need to go down. Okay, near the antenna. Okay, where is your antenna? This is your antenna. Okay, this is your antenna. Click apply. Okay, and where is your antenna? Okay, this is your antenna. Click apply. Okay, so this is your antenna. So you can also rotate your this one like this, okay, at an angle of 90. Then again you can transform, okay. Okay, now you can see this is your antenna, okay. Like I click okay, and you can see here this is your antenna, okay. And behind the antenna you have a human body model, but it is still very large, okay. So we need to crop again, okay. Again very small size, crop again, okay.
And for the hand model?
For the hand model, I do not prefer you to use hand model, because that hand model is just a hand model that do not have the properties of any skin, fat, muscle. You need to you cannot that is the imported file, even you cannot change the properties, okay. So I suggest you to use this human model and use what you need, okay. Like for if you need a human hand or arm, you can use this one, okay. You see, I am using a very small portion of the human body. In this way, your system will be able to simulate this one, okay. And also with this imported file, you can simulate SAR. You can calculate SAR values, okay, in this design, okay.
So I will not get error with SAR.
Yes, you will not get error SAR, but if you import other that already have in CST, then you will get error. But in this case, you will not get error, okay.
Mr. Saros, can calculate the current surface on the human body or the radiation?
On the human body, I am no, you cannot calculate the surface, because you can calculate the E field, H field, or you can calculate the these options, like in the field monitor you have. You can calculate the power loss density, okay. You can calculate the electrical energy density, magnetic density, okay, and E field, H field, like this, okay. Because your surface, your current will flow only in the radiator, not in the inside the muscle and other tissues, okay. So let's check whether we can simulate this file.
You cannot change the color of this human part.
No, this is the same as the skin.
It is by default, yeah.
Yes, this is by default. So let's check whether we can simulate this one, because in most of the computer it gives error when you even simulating your antenna on human body, okay. Because if you take a complete human body model, then there is a very large mesh cells, okay. I am using a very small portion of the human body, so that my mesh cells will decrease.
It has no effect also. If you take a very large body, it may have no effect, because the size of the antenna is small also.
Yes, that's why. So that's why you need to take a very small portion of the human body according to the mesh size, okay, that you can able to simulate in CST in your system. Okay, now if you once it is simulation is completed, you can calculate, go to the post processing, and can calculate the SAR values easily, okay. Okay, also let me check any file that is simulated, I mean for the for you need to simulate this one, okay.
Mr. Sarosh.
What is question of the Ambrush? Request with you is that please take the question after completing the full design CST, because in between we may miss the flow, and since I'm a beginner in CST, will what is your question? Can you repeat your question?
Okay, I'm not the one who tested, but I'm asking my own question. Yes, my question is, placing the antenna on different parts of the body, does it have effect on the antenna, like different parts of the body? Maybe you put it on a hand and putting it on a chest, will you get a different result?
No, because if your antenna is compatible, then if even you are checking your antenna on head, on arm, on leg, on a chest, then you will not find any big difference in the results. Okay.
Okay. So that's due to the fact that the permittivities and the permeabilities are quite not different. So the results will also not quite change. Is that it?
Okay, yes, you are right, but see first which layer is very close to human, your antenna. If you import the complete human body, you will see the first layer comes to near to the antenna is the skin tissue, right? Skin of the human body, and then fat, and then or maybe blood, or then bone, and then maybe muscle. Okay, like this. So you see the properties of the skin will remain the same. So that's why if suppose if you have three layers, okay, like you have a first, you have a skin layer, and then you have other layers. The you see like you suppose you are using two layers. Okay, the first one is the skin layer and the other one is the fat layer. Okay, you see the relative permittivity of the skin layer is very high, is very higher than the fat. Okay, that's why if you have a high relative permittivity, then there will be no much effect of the other layer like fat, muscle, bone, skin. Okay, there will be only major effect of the skin. Okay, because the skin has the higher relative permittivity than the fat and other layers. Okay.
Okay.
Mr. Sarosh, can we calculating the scattering from the body?
What do
It's
you
very important.
what do you mean
Because
scattering?
do you know because all the power, the most of the power is reflected in the body, and just specific absorption rate is the absorbed.
Yes.
Do you know how to kind? Maybe sometimes we need to know the scattering, the matrix of S, because maybe sometimes we need to calculate it in the MATLAB. So we like imaging, maybe like use some other things like that.
Okay. Yes, in CST, I think you will have many options like in the result template. Okay. And also first you are talking about the power radiator and power, that is more important thing in SCR values. Okay, you whenever you calculate the SCR value, you also need to calculate the power. Okay, so in that case you can use the formula, and also you can use go to the field monitor, and you can calculate the power loss and power flow. Okay, in this way you can find the values of the power, okay, radiated. And also you can go to the result template, go to the far field, and you can find the results in the far field. Okay, you will find the option here, I think. If you do not this one, okay, total power radiated and like this. Okay, and you can use any option that you want, okay, to calculate or simulate.
Okay, I think I read some papers about the SAR and power density. For the near field, maybe it's always is used the SAR for the power density for the far field. This is maybe this I read it from many papers, but I want to ask about how to get the scattering. Maybe do you know sometimes when hit the body by the powers, some dispersion, some energy. We can calculate this dispersion by the S parameters. That how to calculate it in the CST if you know about that.
I think actually all the options are not available in CST. Okay, sometimes you need to use a MATLAB code, or sometimes you need to read the research paper to find the formulas from where you can just calculate with the MATLAB code. Okay, you need to implement that formula in the MATLAB, and then you can calculate the from the MATLAB. You need to export the S11 file, and then you can import in the MATLAB. Okay, I will find some research papers and I will send you. Okay, don't worry.
Thank you very much.
Okay, dear Amrish, how to add the space gap between the antenna and skin, fat, muscle tissue, or should it be put behind the patch only, or will it have any change in results? Okay, for the distance, I told you you need to do optimization. Okay, first, okay, parametric sweep you can use. Okay, first you need to simulate the antenna very close to at 0 mm distance. Okay, and if you check if there is a results in I mean there is a difference, a big difference in the results, then you can increase the distance like 2 millimeter. Okay, and then 5 millimeter, and then you can use 8 or 10 millimeter. Okay, it depends it depends on your antenna. Okay, you first I prefer you to start, you can do optimization, go to the in this way like this one. Okay, let me, yes. Okay, suppose this one is the human tissues. Okay, and the first is the antenna. Okay, this one. Okay, how can I do optimization? So I click on the HT, I mean in which I have two layers of skin and fat, and then I go to the modeling, go to the transform. Okay, and you need to see the side view, and you see if you increase, first you need to place your human tissues very close to the antenna. Okay, now you can see at 0 mm distance. Okay, this is your antenna and human tissues. Okay, now I'm click apply. Okay, this is at 0 mm distance. Okay, now first you need to keep your layers very near to the antenna, like at 0 mm distance, and then if you shift on the other direction you will find W. Okay, here. Okay, so you need to write here D means distance. Okay, and click preview, and you will, it will ask you what is the distance you wanna calculate. Okay, you can write here 5 and click OK and click OK. Okay, and you can see your human tissues are at a distance of 5 millimeter from the antenna. Okay, now you can do parametric sweep you can use. Okay, go to the home and click on the parametric sweep, select a new sequence. Oh sorry, there is already a sequence. Click on the new parameter, and then you can click on the D, and you from starting point 0 and the ending point you can take 4. Okay, and give 3 samples here, 3, and click OK, and you can see there is a, it will calculate the values at 0 mm distance, and then 2 mm distance and 4 mm distance, and then you can start the simulation. Okay, and it will calculate at different distance. Okay, from the antenna. Okay, do you understand now? And you will check where it is showing acceptable results. Okay, first you need to simulate the antenna in free space, and then you will check on the human body at which frequency, I mean at which distance it is showing very close results to in the far in the free space. Okay,
Excuse me, Mr. Sarush. There are sometimes the voxel model, maybe in some point in the voxel model in the body, not sensible in CST, not sensible for. I think I want to calculate some electric field there, because not sensible there in CST. I don't know why.
Yes, sometimes it happens also in my CST. You need to simulate and maybe do some animation. Maybe it sometimes happens also in my CST. Suppose if I want to calculate the E field, that it does not show any like E field in my design, but sometimes it happens in the correct versions.
Sometimes I need to grade some point to calculate that. This is or some materials to grade that to find the effective on this point. So the Voxel module like is the air. They didn't catch anything because it's very difficult to deal with it.
Mm-hmm. Okay, wait a minute. You can see here. I did not do much simulation. I just stopped the simulation because it is taking much time. And now you go to the post processing. Click on the SCR values. Okay, if you want to calculate the SCR value at 2.45 gigahertz or 5.8, you need to optimize. Suppose if you have a single antenna, single band antenna, then you click on the 2.45 gigahertz, and you need to calculate the SCR value at the both gram. Okay, or even if you want your own, you can write here point SCR, and you can write, oh sorry, you can write, go to this custom and write here 25 gram or other gram. Okay, but in most of the research paper only 10 gram and 1 gram. Okay, just click on the 10 gram and click calculate, and you can calculate the SCR values. Okay, it will start simulation here and you can easily calculate. Okay, but here this file is not fully simulated, that's why maybe it gave you, or it give you some errors. Okay, so did you understand how you calculate the SCR values? Okay, in this way you can calculate. Okay, these two. And you can also put your I mean your power, relative power. Okay, here. Okay, what was the question? Now you can ask me question.
For Mr. Ahmed, for E-plane and H-plane.
For actually it is not simulated yet because I told you it is taking much time. I stopped the simulation. Okay, the simulation are not completed yet. For the E-plane, I told you for on-body case need a you need a omnidirectional pattern, and for the H-plane you need a directional pattern. Okay.
I mean for I get E-plane, what degree I must put in CST?
For the E-plane it is 90 degree. You know, phi is equal to 90. Okay, and for the H-plane phi is equal to 0 degree. Okay,
Because some article I get, they put 0 degree for E-plane and 90 degree for H-plane. So they confuse me.
can you repeat your? I did not understand.
I get many articles, they put 0 degree for E-plane and H-plane for 90 degree for H-plane.
Can you send me that articles? I am not sure because they maybe they did or mistake, or maybe in sometimes they are not for co-polarization, because maybe they are calculating cross polarization, because in cross polarization it is different. Like if you are want to calculate co-polarization, then you put the E plane and phi is equal to 90 and H plane phi is equal to 0. But if you want to calculate the cross polarization, then it is inverse process of the co-polarization. Okay, you put the E plane is equal to 0. Yes, maybe because of this.
Maybe yes, maybe for that. Okay.
Okay.
And in your case, what do you choose, cross or co-polarization?
I prefer both if you use both. Okay, because sometimes if the viewer may ask question to put the values of both E plane, I mean cross polarization and co-polarization. Okay.
Okay.
And as I told you, a lot of research has been done on this type of antenna, and those who wanna work on this type of antenna, I prefer to target IEEE journal, because IEEE journal accept these type of designs. Okay, and what we can do new here, wait a minute, why there is a line? Okay. Okay, for the wearable antennas, okay, what we can do here, you see here in my this IEEE access, I have used the meta surface, okay, that is another novelty factor. Okay, so we need two novelty factors. Okay, what we can do, we can make the antenna flexible. In my research paper my design was not flexible. Okay, so I suggest you to use Roger materials 5880, okay, or with 0.8 millimeter thickness. Okay, or you can use also use 1.52 millimeter, because in this thickness you can simulate or calculate the banding analysis in simulation. Okay, but in practical you cannot. Okay, but it is still acceptable. Flexible. Okay, but because if you claim that your antenna is flexible, then you need to use a very less thickness. Okay, maybe 0.2 millimeter or 5 millimeter. Okay, because low profile antennas are flexible antennas, so that's why you need to choose a low profile material. Okay, so you can claim this one flexible. Okay, in wearable antennas, and you can the other thing is CP, okay, circular polarization axial ratio. You can also it is better to if you achieve circular polarization in wearable antennas. Okay, and also we can add metamaterial. Okay, in wearable antennas. Okay, and the fourth one is the implementation on human body. Okay, on human body. Okay, we will have these type of for explanation that we can explain and target at IEEE journal. Okay, CP is very important in every design. Okay, that's why. Okay, what is the question in the chat box? If possible, can you send us some of these .csv files that have already been published for the off-body antennas? Okay, I will send you the files. Okay, for this one, this design I will send you. Okay, but I will send you only dual band. Okay, not with this meta material. But when I teach you the meta material, then I can able to send you the meta material file. Okay, and for this one I will find the file, because sometimes when my paper is published, then I remove the data from my PC to have space. Okay, but I will check if I have this file. I will share with you. Okay, you can see this is a very simple design, very simple design. Okay, and it is published in sensors. Okay, this is a Q2 journal. This is Q2 journal with IF impact factor of 3.7 576. Okay, so this is also a good journal at MDPI sensors, but I have a lot of publication in MDPI, so I don't like to publish more in MDPI. I want to target a IEEE journal now. So do you understand? Yes.
Sorry about that. Please, I just want to, if you can clarify something for me. In the copolarization and cross-polarization, what exactly are we looking out for?
Okay, in E plane and H plane you calculate the copolarization that tells you about the, actually both are very close to each other. Okay, both have the same applications, like it will tell you about the E plane and H plane of the antenna. Okay, but with the different angles. Okay, and the other thing in cross polarization, let me okay, let me open that figure to, or you can I can write here. Okay, suppose you have a pattern. Okay, you have a box. Okay, in which you have a far field. Okay, suppose you have achieved the you have E plane and you have H plane. Okay, H plane and E plane. Okay, in both of the cases, copolarization and cross polarization. Okay, you use the same these two. Okay, E plane and H plane. Okay, but with different angles only. Okay, in this way, in the case of the copolarization, you put the value of the E plane, phi is equal to 90 degree, okay, phi is equal to 90, okay, and in the case of the H plane, you put the value phi is equal to 0 degree, okay, and it means yes. And in the case of the cross polarization, you take different values for the E plane, like you use E plane 0, phi is equal to 0, okay, and for the H plane phi is equal to 90 in the case of the cross polarization, okay. They are very same, but just difference in the angles, okay. Also for the E plane, for the copolarization, suppose you have a E plane and H plane of the copolarization, like in the E plane you find a pattern like this, okay, like this, okay. Okay, this is your E plane of the copolarization, and this is your let me draw a different color. This is your H plane of the copolarization, okay, and here you have a scale bar of the realized gain, okay, that tell you about the gain, okay. At the center you have 0, okay, and you have starting from -1, -2, oh sorry, here it is starting from 0, okay, and suppose your antenna has a gain of about 1 or 2 dB, and it will when the last value here it is 2 dB, okay. This is the scale bar of your realized gain. It can be scale bar of your directivity, it can be scale bar of your IEEE gain, okay. In this direction you will have a 2.4 dB, and also here but it is I think in minus, okay, 2 dB, okay. So this scale bar tell you about the gain, okay. And for the values, okay, you in CST when you calculate the radiation.
Sorry, but I want to know what is the benefit when I put this graph in the paper.
You mean this scale bar?
I mean for the E plane and H plane, for co and cross polarization.
Okay, okay, let me complete my talk, then I will answer, okay. Okay, suppose in the first scale bar is this one that tell you about the realized gain of the antenna, okay. And there is another scale bar that is not outside the radiation pattern, it is numbers, okay, that is here in CST. Maybe you will find like -5 dB, okay, like here you will find -10 dB, okay, and here suppose you will find -20 dB, okay, and here maybe you will find again -30, okay, and then again 20 and -10, okay, like this, okay. And this is the case of the E plane, okay, and it may start from the 0 dB, okay, like this, okay. And but if you want to calculate the cross polarization, then it will start from the let me choose different color, okay. It may start from this -15 dB, okay, maybe like this, okay. And its value should be less than for better performance, okay. Its value should be less than -20 dB or -15 dB, okay. For I'm talking about cross polarization, okay. So if you see a graph of the cross polarization, you will find options, or you will find graphs that seem to be very small in size, but if you notice they will start from the -15 or -20 dB, okay. So in this case you can claim your antenna has achieved better performance in terms of the E plane and H plane, okay. And if your value is not below -15 dB or -20 dB, then your maybe sometimes your design, sometimes if there is a strict reviewer, they will reject your design, or they will say to improve the performance of your cross polarization, okay, of the E plane H plane of the antenna. And what was your question of Tariq?
And if I want just choose one.
Yes.
And
Yes.
cross-polarization.
Yes, you can in most of the cases people like to add co-polarization, but in IEEE journals mostly reviewer ask both, okay, for cross polarization. But in my papers I very less time I use cross polarization, okay, but you can see I only add co-polarization, okay, E plane, H plane, okay.
Okay. And this result, can we say that is good or not in your paper?
Yes, they are good, but I did not only add the cross polarization, okay. So you can even see in the E plane and H plane, actually in most of the where here the question is where we should add the cross polarization. The reviewer mostly ask about the cross polarization when your antenna is circularly polarized, okay.
Okay. Okay.
Yes, but in the other cases you can also add, okay, but most of the cases I saw papers that are circularly polarized antennas and they like to add cross polarization, and reviewer ask for that.
And we can measure this.
Yes, we can measure in the radiation pet chamber, okay, far field chamber, okay. So do you have any other question, and did you understand the whole procedure, how to simulate the human body model, how to simulate the layers, how to you see the design is simple, the same design as we study in the first 2 3 lectures, okay, only simple patch antenna design, just we are implementing on the human body, okay. For the we the same procedure to calculate the SR values, okay. You can use if you I use the meta surface, that's why I do not prefer to use flexible material, okay, that's why I use air FR4, and at that moment I only had the FR4 substrate, okay. But the reviewers may ask questions if you are implementing the antenna on human body. They will surely ask you why you did not use any flexible material, okay. So that's why I prefer you in advance to use Roger material for human body applications, okay, so that you will not face any problem in the future.
Alright, so can you please show us the cross polarization or co-polarization of this design, table design you just showing here?
Here I did not simulate the design because it is taking much time because of the human body, okay, that's why I did not simulate the design. It may take more time, maybe 45 or 1 hour.
Alright, so sir, can you show us your PPT where you explain co-polarization and cross-polarization?
Yes.
Sir, you said that E plane and H plane both are 90-degree inverse to each other. Like you see here, sir, for co-polarization, E plane phi should be 90-degree and H plane should be phi value should be 0, sir.
Yes.
Am I right, sir?
Yes.
But for the case of cross-polarization, E plane phi should be 0 and H plane now it should be having 90 degrees, sir.
Actually here you also mentioned theta, okay. I did not describe theta here, okay. You also you need to vary two values, okay, of phi and theta, but in this case I think you keep your theta constant, but in this case of the cross polarization you also vary the value of the theta, okay. I will write the values, okay, in a graph, okay, and I will so that you keep remember in your mind the values, okay, and do not forget in future. I will find the values, okay. I mean the complete values of what should be the value of the E plane and what should be the value of H plane and what should be the value of phi and theta, okay, in the case of co-polarization, and what are the values of E phi and theta in the case of cross polarization, okay. But you should know the way how we can find, but here there are no far field. Yesterday I showed you when you click on the far field like at 2.45 gigahertz you will see many options like phi and theta phi and axial ratio and theta only and phi only, okay. When you want to calculate the co-polarization you will just click on the phi and you will find options here to change the angle, okay, and then you can calculate, okay. You just need to keep the values in mind, okay, to calculate the co-polarization and cross polarization.
Sir, just for double check, sir, can you please show me the PPT of co-pollution, cross-pollution? So where, just please double check on it for cross-pollution. You see here phi is 0 and for H plane also phi is 0.
Oh no no. Sorry. Here I was talking about 90. Okay. I mistakenly write here.
It should be 90 degree, right, sir? I'm confused here, sir.
Yeah. So I was talking about 90, but I did not complete 90 here.
Sir, thank you, sir. Sir, can you please share us, sir, some CST files so that we can make practice? It will be very convenient for us. Whatever you design, share us the CST files so that we can
yeah, actually, you know, when I share the files, then mostly people like to only modify the shape. But I prefer if you design it by yourself, then you will have more experience. Okay, then you will be more expert. Okay. And
but it's something it's difficult for us. We are beginner. I think it's just for we should learn first to run the files. If you give us favor, kindly sir, do share.
Okay, I will check and I will share the files that are published. Okay, and then I will share you the published files. Okay, of the CST files. Okay, and because of we I have completed the we have completed this one today. Okay, the human body antennas. Okay, and when we are going to complete we are going to complete up to 14th March. Okay, we have only yes, we have less days, only 8 days, up to 8 days. Okay, we after this we will start working in these 4 days we will finalize the design. Okay, you will create a new design. Okay, or I will guide you how you can improve, or how what should be your design. Okay, how should be your design, what are the results you need to achieve. And these 4 days we will work on the designs. Okay, everybody will show me your designs that you have done. On the first day I write here design, you can write here design selection. Okay, I have on which type of the antenna you wanna work on. Okay, like some people like to work on okay, let me write here design selection and design and group selection. Okay, okay, in this day we will make a group. Okay, like two people like to work on MIMO antennas, and then I will create a group, or you will make your own group. Okay, to work on together. Okay.
Excuse me, Ahmad, do you have already simulated design for the which we are studying now? Do you have already simulated designs? So we will discuss some of the cross and co-polarization for that.
For the moment I don't have any because these papers published 1 month ago, and I don't have any because these files, when you simulate this file, it takes maybe 4 GB and 6 GB hard, or maybe sometimes 12 GB. Okay, so that's why I deleted that files to keep more space.
Sir, does this idea work like implantable antennas? Like you share a simple model, and we modify it towards MIMO for more gain like that, sir?
I did not understand your question. You are talking about implantable MIMO. Can you repeat your question, please?
Sir, you are sharing us as you are discussing single element implantable antennas, sir. Can we increase the gain and add more antennas towards MIMO of this human body antennas, sir? Does it possible we extend further from single element to MIMO antennas?
Yes.
Or implantable antennas?
Yes, we can. Some people are working on it. Okay, some of the researchers this one, they are working on where is the antenna arrays. Okay, they are working on antenna arrays and MIMO together. Okay, I have seen some papers. Okay, to increase more gain of the antenna. Okay, so we can also do in this way.
What is the difference, sir? In MIMOs we use different ports also. In arrays we use only single port, single power. You know, sir. So
Yes, in MIMO antennas you may have more than one ports. Okay, if you have more than one port, then you can say it is your MIMO. But in arrays you have one port, but you have more than one number of antenna elements. Okay.
For beam forming, different beam forming.
Yes, in antenna arrays it is the port is one. Okay, the same port, one port. Okay, if you are only talking about antenna arrays, not antenna MIMO antenna arrays. Okay, I am just talking about simple antenna arrays. Mohammed Zubair, you want to say something? You open the microphone.
No, it's okay. I mean the MIMO antenna. Then you clarify that question also.
Okay. Yes,
Do we have any formula? So do we have any formula for MIMO antennas? Like it depends on certain matrices, like 2 by 2 or 2 by 3 or some.
No.
Some matrices.
Yes, it's like matrices, and they are that is the just a technique. Okay, and people are now working on different, like as I told you, in CST and in antenna designing you are open to work. Okay, and you need to find a new technique how you can make or create a MIMO. You will see many papers, people are trying to make different shape of the MIMO and to achieve novelty aspects. Okay, so even in our case we can design different shapes of the MIMO antenna just to connect the antennas in different ways. Okay, and different antenna elements. The most important thing in MIMOs to keep the size compact. Okay, and to achieve more better isolation. Okay, and other thing is what is the other thing, and connecting the ground planes. Okay, because in MIMO antennas when you connect the I mean if you use common ground plane, then you will not have much good results. That's why people do not like to use the ground planes, because common ground plane I mean. So you need to apply a new technique that connect the ground planes. Okay, and you achieve more better results.
Mr. Ahmed, did you work on what we say substrate integrated waveguide before?
Yes, I have a research paper, but it is not published yet.
Can you tell me just what is the benefit?
This is a substrate integrated waveguide array. Okay.
Because I want to work it in it.
This is a substrate integrated waveguide. This is also circularly. This is a very good design that has many novelties. Okay, even it is very simple. This is a wideband. The first one is wideband. The other one is it is circularly polarized. Okay, and the third one it is CPW fed. And this other thing is it is a substrate integrated waveguide. Okay.
Okay, just tell me what is the benefit when we use
okay yes, actually substrate integrated waveguide help you a lot to increase the efficiency of the antenna, and also it help you to increase the gain of the antenna. It helps a lot in increasing the gain of the antenna. Okay, and you can use this one. Okay, this is another technique, substrate integrated waveguide, and you can
we make just a hose in the substrate. Yes.
There are two types of substrate integrated waveguides. The first one is the just creating holes. Okay, but that technique is not called substrate integrated waveguide. In that case you need to, like in this paper you see where is the design, and also let me you can see here maybe there is a shorting pins. Okay, in this
yes.
You can see that connects you should have the same structure as in the ground plane as in the patch. Okay, and then you need small holes inside, and then you connect the shorting pins that connects the ground plane and the patch. Okay,
and these techniques can is help me for reduce the surface wave.
Yes, you can use this technique. It has so many benefits. Okay, it also help you to reduce the size of the antenna. Okay, it also help you to increase the gain of the antenna and efficiency of the antenna. Okay, and you can try this one. Okay, also it may help you to improve the radiation pattern.
So we have two methods. Make a holes in the substrate and these pins.
Yes.
Okay.
But
Thank you.
yes, I suggest you to use this one because even if you are designing simple patch antenna, if you create hole, there will be no big difference in the results. But if you are connecting the shorting pin, then you will see the difference. So that's why I suggest you to use shorting pins. Okay, as you see, these shorting pins are connected the ground and the patch. Okay.
Yes, but I see that you make holes and also in the patch.
Yes, they are just holes to insert the shorting pin. Okay, to connect it.
And this hole is connected with the ground.
Yes, that holes, you insert the shorting pin, okay, from that hole, and then you solder the patch and the ground. Okay, the shorting pin with the patch and the ground. So in this way you will find more better results. So that's why I suggest you to use shorting pins. Okay.
Okay, thank you.
Sir, in almost all kind of antenna design, sir, you're using CPW technique, CPW field line, sir.
Yes, I am using.
So so actually I missed this CPW lecture. In which lecture you covered this? In lecture 2, 1, like.
In my each lecture I just talk about the CPW. I like this technique, that's why I am using this CPW, but in some of my designs I use different techniques. Okay, in my next design I am thinking to I have some design, but they are not published on the they are not based on the CPW. They are really new designs, and I hope you will find in futures, I mean new papers in future. They are very new technique. Okay, and nobody has applied like that. Okay, so I in antenna you can use any technique, but just remember about the ground plane and the I mean the positive point and the negative point of the connector. Just keep in mind.
Okay, sir. So what is the short definition of CPW? Like
short definition of CPW is that you are using a ground plane and the radiator on the same side of the substrate. Okay, you see this is the radiator and this is your ground plane. This is on the same side of this substrate. Okay, because in most of the cases you use ground plane on the other side of substrate that connects the connector. Okay, I mean at this portion, not on the other portion. This is a defective ground. Okay, it means they are not a part of this port. If this is not a with the port, then this is not called a connector. Okay, sorry, ground plane. Okay, the portion of the CPW or the ground that connects with the connector is called ground plane. Okay, so you see both are ground plane and the radiator are on the same side of the antenna. Okay, and CPW help you to, there are so many benefits of the CPW. The first one, it helps you to keep the size of the antenna compact, because the size of the antenna mostly depends on the length and width of the CPW. Okay, if you and also you can vary the frequency very easily with this length or width of the CPW. If you increase the length, if you increase or decrease the length of the CPW, you can control your frequency. If you increase or decrease the width of the CPW, then you can control the bandwidth of the frequency. Okay, like if you increase the gap, you will find more bandwidth. If you reduce the gap, it will become a narrow band. Okay.
In this design, the patch in the left and the right side,
yes,
they are not fitting. How they are radiated?
You mean this one?
Yes.
Actually this is called parasitic elements. Okay, that is not a part of the radiator and the ground, but it help you to increase the gain, or it help you to increase the efficiency. It help you to even control the what will happen if I do not use this plastic elements. If I do not use this plastic element, my gain will not improve, and also my radiation frequency will not set like at I have a frequency, my antenna is resonating at 5 gigahertz, and I want to reduce the frequency band at 3 gigahertz. There are many ways to reduce the frequency band. The first one is the most commonly method to increase the size of the antenna, but I do not want to increase the size of the antenna. I want to keep the size of the antenna same, but what technique I can apply to achieve the lower bandwidth, lower frequency band. So that's why I use these plastic elements. And some people ask, how do you know the length and width of these plastic elements? I added the very small size of these plastic elements. Then I use parametric sweep to optimize these length and width of these plastic elements. Okay, and I decided at which size of the plastic elements the antenna has good results. Okay.
And sometimes I get they use CPW with the ground in the same time.
You mean CPW on the same side of the
And
connector?
ground. Yes, they call I think coplanar waveguide grounded.
Yes, there is another technique. Okay, you can see here in the macros, go to the line impedance, you will find option this one. Okay, you can see this is your CPW,
Yes,
and this
exactly,
is
that's
your
what I mean,
field
yes.
line, and this is your ground pin. Yes, you can use this one too, but it is not I mean very less researcher use this technique. Okay, but it help you to control the back radiation, because in CPW you will have a problem of the back radiation. Okay, so this
Yes,
ground plane
exactly,
may help
yes.
you to improve the radiation pattern.
Yes, thank you.
But it is you see, if you look at this view like this one, you will see it is just like that one. But you don't know where is your ground plane. It is on the upper side or it is near to the port, but I use here to control the radiation pattern. Okay, and also I use this one because of the because I am implementing this antenna on the human body, and to reduce the back radiation and the achieve more less SCR values, okay, of the antenna.
And why you choose these circular shapes?
Why I use, okay, so here in this paper I use the optimization results of this where is this one? This one, you see there is a contribution on the frequency band. Okay, if I increase the length, like if I pick this both circular rings in the upward and downward, then you see there is a shift in the frequency band. Okay, you can see. Okay, that's why to control the frequency band I use these circular rings.
So can I make like SRR?
Yes, you can make SRR. It's up to you, whatever you do want to do.
It means that for the defective ground we can use any type of
Yes.
material.
Yes, I mean any shape. It up to you. As I told you, in antenna designing, it's totally up to you. Okay, but you need to check at which shape you are able to achieve more better. Because you don't think that I only use this one. I use many other techniques, like I use partial ground, like on the upper side of the substrate, and I check the results. I did not find any big difference in the results, or my results are not good. That's why I tried many different shapes here. Okay, and with this shape I noticed that I have good results. And one more important thing, people do not know where we should create these circular rings. It can be in the mid of the substrate, it can be on the top side of the substrate, it can be on the bottom side of the substrate. But why I use only at this position? Because if you want to make a defective ground, then I prefer you to create this if you want to make a circular rings, then you need to create this circular ring on the opposite side of the radiator. Okay, you see I have a radiator on this side, and this circular ring on the upper side of the on the opposite side of the radiator. Okay, so it will give you some difference in the results. It may help you. Okay, otherwise if you use on the opposite side of the field line, then it may not affect much. Okay,
but why you not shifted this radiating above some above?
what?
Why you don't shift this radiating element in the ground, like left or right? You make it in the middle.
Yes, you see the width of the substrate is not very large, so even if I shift right or left, it may not have, it will have the same results. Okay, only difference in the result if you move it up and down. Okay,
okay,
so it is on the back side of the radiator. So whenever you want to design, I suggest you to design on the opposite side of the radiator, not the field line. This is the radiator. Okay, the monopole. What material do you use for plastic element, not a plastic element? The same as copper. You see the for the same as for the ground, for the same as the patch. Okay,
okay, I understand now.
yes, and the spellings are this one. I think plastic, parasitic. Okay, not plastic. Okay, so you have any other question, or we leave the session and meet tomorrow? Okay, I hope you understand most of the things. Okay,
So last question is how we can validate our implantable antenna, like from the results of ESWRS11 or from far field radiation pattern, polarization pattern result. So or कौन से factors हैं मतलब I mean what are the further factors to validate our implantable antenna?
it depends on the antenna application. Okay, if you want to MIMO antenna, then your parameters, actually these as parameters, and the surface current and the far field are the same in every case. Okay, these are most commonly used parameters that on which your antenna base. Okay, if you use other parameters, according to the application, you need to add more results. Okay, more parameters. In MIMO antenna you add S21, you add ECC, you add CCL, many other parameters. Okay, it depends on the application, but in normal cases you like to add only S11, efficiency, gain, because only these matters depend on the design and the efficiency of the design in the working condition of the design. Okay.
Alright, sir. Sir, how about the results from? We see the results of this antenna design from your paper, or you will show us by tomorrow?
Can you repeat the question? I did not understand what you mean.
So we since this model didn't simulated completely, so I just want to see the results. So you will show us the results of this antenna design by tomorrow, or we see from your paper like these are the results like usual?
You need to follow the research paper first. Okay, I just told you because we already know the designing procedure, and now it's up to you to design. Okay, I am just working on the applications of the antenna. Okay, because you the design, how to design it, you learned this thing, okay, in the previous lecture, but now we are discussing the applications where we can implement this antenna. Okay, so that was the important thing we discussed today about the how to import, export, simulate, and calculate the SAR values. Okay, and calculate the properties of the antenna. Okay.
Right, sir. Thank you, sir.
in the other lectures we also discuss many other things. Okay, so we have many interesting topics. Okay, implantable dielectric resonator, MIMO antenna arrays. Okay, millimeter wave antenna reconfigurable. This is very good topic. Okay, and also metamaterial based antennas. Okay, and then we will discuss about the professional graph tools, in which we in this lecture we will discuss how to make high resolution graphs. Okay, of both S11 or radiation pattern or of the structure antenna shape. Okay, and then on the next lecture we will decide, I will give you 3 days, okay, to work on and finalize your design. Okay, and you need to show me your design on each day, what is the progress, and you have to work on it. Okay, and you need to complete in 3 days, and then we will start the research paper. Okay, writing the research paper. During this writing, once your design are finalized, I will send these design for fabrication and measurements, and then we will complete our papers. Okay.
Mr. Sarosh.
Yes.
The journal, they accept 300 or 600 dBi for the graph.
The more 300 dBi is common, but it depends. Actually, every in graph it is you see everything must be clearly visible and readable. Okay, you can see this is easily readable, so this graph is acceptable. Okay, if you think the graph is readable perfectly, then it is acceptable. Okay, what our next task, I mean regarding the research papers, we have 7 days, I mean 1 week for writing research paper, and the target is conference paper. Okay, conference and journals. Okay, and here question rises, which journals we should target. The first one, I mean for the journals, it depends on the design of the antenna you have made. According to the design and paper you have written, I will suggest you some journals. Okay, where we will submit the paper. Okay, but I want from you to work on journal, because I am teaching this course only to teach you these things and to make a strong research group. If you successfully attend this course and able to write a good journal, then I will surely allow you to work with me for a long time. Okay, and for long time surely we will have many research articles, not only one. We may have many articles. Okay. Okay, we can end the meeting now. It's up more than 2 hours. Okay, 2:20 to 2:15 hours. Okay.